Hi there, welcome back. So let's move to the last case now regarding numerics, this short review on numerics. So this is I would call it the numerical schemes killer, this SOTS Chuck 2. This is a personal favorite case. I love this case. So as I mentioned, this one has an analytical solution. So also we'll put here in the web page the link for the IPython notebook where you can compute it's using a set Riemann solver just to compute this solution. So here you have the Python script now just to compute this solution. Okay, so it's a relative short. You have the reference. This is a very good book. So this is a completely different tier, okay? But it's a very nice book. I invite you, if you have time, just to review. And this is the solution, okay? So this problem has this solution, okay? So see that what is interesting is this solution. See that here derivative gradients, they are not continuous. This is a killer. These are discontinuities, and this is difficult to solve. Okay, all the pressure, velocity, temperature, density variables, everything. Okay, see that have these strong discontinuities that they are really difficult to solve numerically. And there is also that is difficult to solve. See that then in density. Also, you have these discontinuities. These are called now contact discontinuities, which are difficult to solve as well because you have a discontinuity in density that is not accompanied by a discontinuity in velocity. So this particular one, see that density, okay, this contact discontinuity, but then you have constant pressure there and constant velocity. Okay, so these are tricky to solve as well. So we have this analytical solution. So this is fully unsteady problem. We're entering into the hyperbolic domain. You need to have that time derivatives. One, by the way, in Navier-Stokes equation, they are hyperbolic, but as you don't have these strong discontinuities, you can get your way around with a steady solver. But when you start to have shockwave stuff like this, you need to put time derivatives, otherwise it's very unstable. So we're going to run this one, and we're going to do the sampling and allocation of the domain at 0.1 seconds. And let me introduce you the problem. So this is what we have. Okay, so now we go out those simple equations, now the general transport, and we're solving the actual equations. Okay, so these are the older equations. Remember, they come from the Navier-Stokes, but you will eliminate viscosity. Okay, so we don't have viscosity, we don't have turbulence in this case. Okay, but if you want, also you can enable the fully viscous and you can get the same solution. Okay, it's applicable as well. So this case is very nice because you have a lot of experimental numerical data. So basically this case is something like that you have a high pressure tube, you have a kind of a wall here, a diaphragm node that you break. You have high and low pressure. When you break that wall there, that diaphragm, you will have the shock wave system moving around the shock tube. Okay, so it's something like this. Initial conditions. Okay, I will call region 4 and 1, and these are your initial conditions. So see that everything is stagnant, nothing is moving. Okay, but you have that large pressure difference between these regions and also a difference in temperature. Okay, so when you break this diaphragm, what you have is this shock wave system. So you have an expansion fan, a contact discontinuity, and a normal shock. Okay, all of these shock wave are difficult to solve. Okay, so here's where you start to see how good are the CFD solvers and also the discretization methods that you use. Okay, so see that you have all your discontinuities, and here I'm showing you a comparison already now of a solution obtained with Fluent. Okay, so see that we have a very good agreement. Okay, so when we talk about accuracy, see that accuracy means that you need to resolve those profiles. So now as you use a first order method, you will see that you lose accuracy. Okay, also if you use quartz meshes, also you lose accuracy. But also boundedness means that you need to have, you cannot have oscillatory solutions or unbounded solutions. So see that probably here you have a small peak there, and that might be solved using a different technique, okay, or a different gradient limiter, stuff like that, but we don't need it here. Okay, this is not a big deal. Okay, so this is an accurate, robust solution. Okay, so let's work it out in this case. Let's see how to set up this problem. Okay, again, you will have, let me launch Fluent. Okay, I have it here. And in the cases that you download, you will have another folder called Fluent SOD, SOD. And you have the geometry here. Okay, so it's a quartz mesh. And here you have a refined mesh. And then here also you have the solution, okay, that you can read to compare. So let's launch Fluent again. launch in double precision and invite you to run this case in single precision, and you will see that you will have some accuracy problems. Okay, so always enable this one. As I say, I don't see any reason why not to choose to enable this. You don't require to run in parallel. So let's start here and let's see how to set up this case, because there is a peculiarity. We already have seen that, but just to remind you, see here that we need to have a non-uniform initialization, because here you want these pressure and temperature values, and here these pressure and temperature values. So I just want to remind you how to do that, but we have seen that you create the region and then you patch your initialization and then you let it run. So if I open the case, okay, so why is not opening in that directory? Okay, I pick up the wrong directory. Let me close there. Let me reopen. So it should be working SOD. Yes, that is SOD. So let me launch here. You can work in a different directory, but it's better just to work in that one, because also Fluent will create some files with the trace that you have here in the terminal. So it's better to have it in your working directory. Okay, so let me go here, case, and let me open the 100 cells. Okay, just to mention about that trace file, this, if you are wondering what is this file, TRN, this is where you have everything that you put in the text user interface. You have it there. Okay, so you have kind of saving whatever you are doing here. You are saving in that file. It's automatically saved by Fluent. You can disable that, but it's not a big deal. It's better to have it. So see that you read that one and we go. It's a transient case. Okay, see here that viscous, you're choosing visit. Okay, so Euler equation, put your energy equation. Okay, so all the other models disabled materials go to air. You don't have viscosity, but you need to define here your density. Okay, ideal gas, CPU, molecular weight, everything. So you want to add passive scalars, you know how to do it. You know, you have seen how to do source there. So if we go here, nothing to do. Okay, so see that nothing, no source there, but we set up the air there. Now we go boundary conditions. Okay, so we have an inlet, outlet, and walls. Okay, symmetry, top, bottom wall. So if you go into, okay, so actually, yeah, everything is symmetry because this is a closed box. So yeah, probably I chose the wrong names, probably because they are not very intuitive. If you see inlet, maybe you are going to guess that something entered, but it's inlet, and symmetry. But everything is symmetry. Okay. All the walls are symmetry. You can put also wall because you don't have viscosity, so you are not going to have shear stress. So it's a closed box. Okay. Nothing to do here. And then you go here in methods and see here that you have now pressure, density, momentum, energy, okay, and your time derivative. And these are all corrections. Remember when we were talking about numerics and gradients, all that stuff, those are corrections to increase or to reduce the errors, increase accuracy. Okay, so let's run first using everything second order accurate. This is how I recommend you, like this. Second order accurate, remember, time derivative, you can leave it first order if your CFL number is lower than 5. You are not adding too much diffusion. More than 5, maybe you are starting to add some diffusion. Here you see that I'm monitoring the CFL number and self-register. So to do the initialization, just to remind you, so you go here, you have region. So I have to self-register. Region 0 and see save displays is just choosing this part of the box where I'm going to patch some values, and region 1 and choosing the whole domain. So probably I can use this one to refine my mesh, which is actually what I did. No? Then to initialize, see that you go here, initialization. So everything is uniform. So initially you are putting these values. Okay, see 1. Now you're going to select this part of the domain and you're going to put this value. So remember that part of the domain is region 0, this one. So when you initialize, you have here the option patch. We're going to patch what? Region 0, I want to patch with this pressure value and with this temperature value. Okay, it's already preset up. So as you go here in graphics, see that you go velocity, see everything 0, but then you check temperature, see that you have your definition. So see what is happening when you break this wall here, you have the shock wave propagating in both directions. Okay, so this is a very severe problem. Okay, so we're going to sample along a line here, okay, and at time 1 second. Okay, so we're going to reproduce that analytical solution. So we have that, and let's run. So see that I have this time step, okay, and if I go here, calculate. So I have my default tolerance for the monitors 10 to the minus 3. Remember that is okay. And see that it's converging like in 8 iterations. 5 is changing a little bit, but this is ideal. See that my CFL number is about 0.1. So this means that maybe you can go higher in your time step, okay? But this is a severe problem, okay? So maybe it's not a good idea to go higher. But see what is happening here. Look at this oscillation. So this is telling you that this is not an steady problem, because from iteration to iteration is changing, okay? So now if I go here, and here, well, you have the solution, and see that you have your temperature, your evolution of the solution, you have everything. So if you go now sampling, okay, here, I created already the line. Let me go here, and here we can do the sampling, okay? So see that I go first velocity magnitude. You have this profile. Let me load the analytical one, Solver, and as you compare, you have it there. So it's a very good agreement, okay? So see that here is a little bit oscillatory, but for the time being, let's not worry about this. So now let's do it also with temperature, okay? This is another critical one, okay? So let me load temperature profile, which should be T, okay? And here you have it. See that it resolved very well here. So this is, as you can imagine, that here you have this strong discontinuity. Okay, derivative there you have problem computing that because they are not continuous anymore. Okay, so this is the numerics. So see that we have a relative good solution. So let's do now, and let me show you what is the problem. In this case, if I go, for instance, if I go now and put everything first order accurate, okay, so it should be density, first order. So remember that this is super robust. It will give you always a solution. The only problem is that you are losing accuracy. And we're going to see that in particular with these profiles, that they are going to be smooth. Okay, so now I have this, and let me run, calculate. See that it's going up, then going down, arriving to the convergence criterion, going out. Okay, so from time step to time step, it is converging the solution, but it's not going down like in the previous cases that you have a monotonic, okay, convergence, but that is monotonic because it was a steady case. This is clearly on a steady case, so you are not going to find that monotonic convergence. Okay, so it's running. Let's see, we'll stop soon. Now we have this, and let's do the sample first in temperature. And see that already, you see that there is a large difference, okay? So if I go Sol T, see here that this is numerical diffusion. So it is smoother, however, it is unacceptable. And this error here can account by as much as 20-30%, okay? So don't be fooled by the fact that when you put everything first order accurate, you're getting convergence, okay? It's true, you're getting convergence, it's very robust. You're getting convergence, it's very robust, but you're losing a lot of accuracy, okay? So we can do the same for velocity, okay? So see velocity as well. So no, oh, sorry, velocity should be here. And see clearly, you see a different profile there, okay? Okay, so be careful with the accuracy, okay? So now we're talking about discretization, and this discretization refers to each term that appears in your governing equation. So here you see clearly that you have a time derivative, convective term, diffusion term. Here you have also gradient and source term. As you go to the Euler equations, see that the same terms you have it, okay? you have the exactly same terms, okay? So you're applying the same treatment there. Okay, so now let's move and let's do something here. Okay, let me go default here and choose default method there. Okay, so by the way, here, now that you are solving the pressure velocity coupling, now you're going to see here. So when you go on steady, I recommend you to stay in the piezo, use the piezo. Again, you can, in this case, you can play around with all the methods, okay? You will find that the piezo is the best one. Probably also you will find that couple is really good one. But the problem with the coupling on a steady problem is that it is too expensive. It will use a lot of memory, and generally it is much slower than the piezo. Okay, so the couple is something that I recommend you. You are running steady simulations, go for the couple. Remember that you control steady simulations using the under-relaxation. However, if you're running on a steady, use piezo, okay? It is less expensive, and then you have different variants of the piezo. You have like non-iterative time advancements. This one is something that I'm going to address when we talk about less. For this case, I don't recommend you to use. Okay, so this is the recommended one, and see that I want to show you that you have different methods. So see that you have first order accuracy. So let's choose a first order accurate method. Okay, so now we have more accuracy. Let's see what happens when we choose a higher accuracy. Okay, so it should be more accurate, but maybe it will be a little bit more oscillatory. Who knows? Let's run. Let's run. Okay, so it's running. You don't see anything strange. By the way, you can put animations here. I'm not putting animation, but it's the one you can put it. But remember, usually you put those animations and you slow down and stuff. Or you can save everything to NSYNC format. And again, that one also has the tendency to slow down since. Okay, so it's running. Your CFL number about 0.1. Good convergence. I don't see anything strange. And we should be arriving soon to 1 second. Okay, so now we have a first order global accuracy, and let's see what happens in this case. So see that now here we have more, a little bit, as you compare with the previous one, maybe it's a little bit more oscillatory, but we have better accuracy, okay? Again, it depends what you are doing, but generally speaking, second order accuracy is more than enough, okay? So there is no need to go for this extra accuracy. Okay, so the other thing that I want to show you now, so let's go back here and let's go back to everything second order, okay? But now let's play around with the time step, okay? So let me show you the influence now in time with the time step. So let me initialize again. So here we have a low time step. Let me increase it by an order of magnitude. You will see that it will be much faster, but maybe will iterate more, okay? And it might be a little bit more oscillatory. So see that your CFL is about 1. It still is okay, and see that it converges much faster. Probably each iteration, it took more iteration, but time steps, an order of magnitude less time step than using the other method. But if we compare the solutions, see that we have this, okay, and this should be this one. Temperature, no, should be this. Wow, okay, I don't know. Let me load again. No, it's not you. Remove, it's you. Okay, so see that what happens, it was converging perfect, really fast, but see that you lose accuracy because you were using a time step that it was too large. So now this is numerical diffusion due to the fact that you have a time step too large. Again, it's up to you now to see if this is acceptable or not. So most of the time it's acceptable. So again, this case that we're solving is something that rarely you're going to find in actual applications. So actual applications, you don't see such a big difference, but it might happen. So now let me go. So if I want to increase now the accuracy, see that we were solving first order. So now let me go second order. And better a bounded. Okay, bounded is to avoid oscillation. So this is the one recommended, a bounded. And let's initialize again. You initialize, we patch, and we patch, and let me run here. Again, everything is smooth. It is converging. The iterations you see that are converging, and we have a solution. Very fast. And you see that we gain some accuracy. Okay, so this is temperature. If you recall the previous one, now we have a little bit more accuracy. Okay, so see that it is a compromise. Okay, and in some cases, like in this one, is you start to go CFL. Is you go here for an even larger CFL, you are going to miss the whole solution. Just to show you. So as I was saying, it is a compromise. Okay, time step. Okay, with the order of accuracy. So if I go here and let me initialize again, let me leave. So I'm leaving second order accuracies for time. That you see that we have an improvement there, a clear improvement. And let me go here and let me go even higher. So if I go another order of magnitude, no, it's too large. You see that 0.1, you will arrive to the sampling time in just one iteration. So that is too large, okay? You are not propagating the solution. So probably here you get clear the idea. But if I do 0.5 in 2 iterations, I will arrive to my time. Let's see what happens. 1 and 2. So now if I go and then if I sample, see that basically you are missing everything. So this is rubbish. At this point, this is garbage that we have here. Okay, so you advance super fast, but see that you are missing the whole physics. And probably kind of you are capturing these peaks, but this is very inaccurate. Okay, so let's see also another field. Let me see velocity field. So see that this one is completely okay. So see that you kind of capturing, see here that you have a large peak, but this is a problem with very large time step. Okay, so if I go back to, let me go back 0.5. Okay, so this should be okay. Let me initialize. Let me patch. Okay, and let me run here, calculate. So this should be faster than the initial one that was 0.001. Okay, and it should give good results. Okay, so now let me go here and we see that we have good solution. However, we have kind of that oscillation that there, this peak here. Okay, so these are oscillations, so sometimes called wiggles or Gibbs oscillation, but you have this one that depends on what you are doing might or might not be acceptable. Okay, so for instance, you're doing cases that where this value that you are reaching here represents a chemical reaction, so this is unacceptable now because you are triggering an artificial reaction. This case we don't have that, so it might be I might get my way around that. So if I want to eliminate this one, I can reduce my time step. Okay, or I can increase my mesh. Okay, a finer mesh have the tendency to also to smooth things, or I can choose different numerical schemes. The final thing that I want to show you as well. So now we're in time, but see that we can also use under-relaxation. Okay, so when you solve in time, you control by the time step, your physical time step, but also you have the under-relaxation, and the under-relaxation is controlling. You see here that you have this kind of cycling here. You are controlling this inner iteration, so it will have the same effects as we observe in steady simulations. So usually see that these values are too large. So likely if I put this one 0.707, it will improve the accuracy and the stability. And usually pressure, you leave it like this. So this is for me, it's a default setup for unsteady cases. Okay, again, if you put values too low, you're going to lose time accuracy. I'm going to show you that. So let's see what happens with these values. What happens? So let's remember this peak there, and let's see if we can get something better. Okay, so we have a solution, crossing fingers. No, we didn't improve we didn't improve the solution. Okay, but now to show you that if I go here and if I do this to put lower, this it will have the tendency to stabilize everything, but you might start to lose time accuracy. Okay, so let's see what happens. If I go here, and calculate. So see that you already see an effect here, okay? Clearly you see that it's not converging to the 10 to the minus 3, we're having convergence. So we're slowing down everything. And if I sample here, see that it has an effect that is smooths out things, but what was, okay, that was temperature. What's this one? Okay, no, I actually see that it added a lot of dissipation. So dissipation usually is an indication of robustness because you are eliminating all those oscillations, but it's too much. Okay, so there's a way to stabilize, but it's too much. So be careful here. So in theory, probably if I go 0.5, 0.5, 0.5, this one should be a good compromise. 0.5, 0.5, and 0.5. So as you see, these are small cases, super fast, that I encourage you to play with these cases or look for other cases where you have analytical solutions and put into practice these concepts. And now that you have that, let me go here. So it is better than the previous case, but it's not as good as with the large under-relaxation. So as I go here, temperature, let me see. Gosh. What data should be this one? Okay, so see that it's better, a little bit unbounded, okay, but it is getting better. Even if I look velocity, I still have this peak here. So this is it when it comes to this auction. So this was what we're exploring here. First, methods. So basically when we're choosing this, when we're playing around with the accuracy, it's very important to remember that you need to have second order accuracy, in particular for momentum and energy equation. Then you're going to have the turbulence equation that there you can put first order, okay? It's up to you. Then also time derivative, okay? So if your CFL is less than 5, usually first order is okay, but larger than 5, it's better to increase it to second order. But again, depends, it's very problem dependent, like we saw in this case. And to control the solution also, you can do it, the steady cases, you can do it using under-relaxation, but also remember under-relaxation, they also have an influence on the steady problem. So usually here is recommended to take default values, but never put it 1 because it's too large. So usually good practice 0.3, 0.7, 0.7. Again, these are problem dependent, okay? This doesn't mean that this does not mean that they are valid for all problems. It depends of the problem, the physics involved. So that's all for this. This again was a brief review of the basic numerics. So from now on, we're going to move into the turbulence war. Everything turbulence here, I'm going to give you just the cases, no more measures, and remember this theory, okay? This basic numerics that sometimes might be important here, and in particular on the relaxation when doing runs, many times happens that the equation, the problems that they do not converge, but it's just due to the fact that you don't know or you are not controlling the under relaxations. You are in a steady. If you are on a steady, the critical part will be the time step. So that's all. Thank you very much and see you next time. Bye.